Today in this class, we are going to discuss about uh, conjugate of a matrix, the types of matrices. We have to discuss about some basic concepts in matrices. In that, already yesterday we discussed about up to transpose of a matrix. Now, what about the conjugate of a matrix? Conjugate of a matrix is for complex matrices. If the elements of a matrix is replaced by its complex conjugate, suppose for example, if you consider x plus iy is a complex number, the conjugate complex number of that value is x minus iy. Based on that concept, we have to replace the elements of a matrix by its conjugates called conjugate of a matrix. That means that the matrix is obtained from any given matrix capital A on replacing its elements by corresponding conjugate complex numbers is called the conjugate of a matrix, and it is denoted by A bar, is superscript bar, or A over bar. Suppose here we come across some basic properties or basic operations in this conjugate of a matrix. If A bar, B and B bar are conjugates of capital A and capital B respectively, then A bar whole bar equal to A. And in the same way, don't make noise. If you have any queries, you will ask, or otherwise don't make noise, please. A plus B whole bar equal to A bar plus B bar. In the same way, if K is any scalar or a complex number, Ka whole bar equal to K bar A bar. If K is any real number, this is nothing but Ka whole bar equal to K into A bar is any complex number. If AB whole bar equal to B bar into A bar, this is the basic properties on conjugate of a matrix. Suppose for example, let A equal to 1 plus I, 2, 1 minus I, minus 1 plus I, 2 plus I, 3, 3 minus 2 plus I, 3 minus 4I. These are the values. These are the values. So these are the entries of the matrix. Then A bar is obtained as. What about the complex number? What is about the conjugate of 1 plus I? Conjugate of 1 plus I.
1 minus
1 minus I. So this 1 plus I is replaced by 1 minus I. 2 is a real number. That's why the conjugate of 2 is also same. 1 plus I conjugate is 1 plus I. 1 minus i's conjugate is 1 plus I. So that is the way to replace this matrix. These entries of a matrix by its conjugates is called the conjugate of a matrix. So A equal to 1 plus I, 2, 1 minus I, minus 1 plus I, 2 plus I, 3, 3 minus 2 plus I, 3 minus 4I. 1 plus I conjugate is 1 minus I, 2 conjugate is 2. If the 2 is a real number, 1 minus I conjugate is 1 plus I, minus 1 plus I conjugate is minus 1 minus I, 2 plus I conjugate is 2 minus I, 3 conjugate is 3 because 3 is a real number. 3 conjugate is 3, minus 2 plus I conjugate is minus 2 minus I. 3 minus 4I conjugate is 3 plus 4I. So The conjugate, if a matrix is obtained, the conjugate of a matrix is obtained by replace its conjugates, its complex conjugates, then we get the conjugate of a matrix. Now we want to obtain, what about the conjugate of a transpose, conjugate transpose of a matrix? Conjugate transpose of a matrix is nothing but, if this is a conjugate, of a matrix, in this conjugate matrix, we have to change the rows into columns and columns into rows. We get the conjugate transpose of a matrix. That is A bar whole transpose. A bar whole transpose is defined as, or A transpose whole bar equal to A power theta. That is nothing but the conjugate transpose of a matrix. Are you understand?
Yes, sir.
Yes, sir.
Sir.
This is A bar. From this A bar, we have to change the rows into columns, or vice versa. Then we get the conjugate transpose of a matrix, and it is denoted by A power theta. A power theta is nothing but A dash whole bar, or A bar whole dash is nothing but A power theta, where A dash is the transpose of capital A. So for this conjugate of a matrix and conjugate transpose of a matrix is for complex matrices only, not for real matrices. So here also we have to we have some basic properties. A power theta equal to A dash whole bar, or A dash A bar whole dash. That is nothing but A dash is called the transpose of a matrix. From this example, we have to obtain conjugate transpose of a matrix. Let A equal to 1 plus I to 1 minus I. The conjugate matrix is nothing but A bar. That, or otherwise we have to, already we have A bar. Now we want to change A dash. A dash is nothing but this row into column, columns into rows. That is nothing but 1 plus I, 2, 1 minus I, 1 minus 1 plus I, that is nothing but column, 2 plus I, 3, and 3 minus 2 plus I, 3 minus 4I. So here, from this, we want to replace this conjugates of this A dash, replace this conjugates of this A dash, we get 1 minus I, 2, 1 plus I, minus 1 minus I, 2 minus I, 3, 3 minus 2 minus I, 3 plus 4I. So here A power theta equal to A dash whole bar, or A bar whole dash, is nothing but A power theta. And here we come across A power theta whole power theta is nothing but A, because the conjugate transpose of the conjugate transpose is nothing but the matrix itself. The matrix itself, or otherwise, if the given matrix capital A is a real matrix, A power theta equal to A dash only, because A bar is nothing but A in that matrix, then A dash, A bar whole dash, or A dash whole bar equal to A dash only. So this is the basic basic properties or basic concepts, conjugate transpose of a matrix and conjugate of a matrix. Next, we want to discuss about lower and upper triangular matrix. This is already known to you. Already in yesterday class, we have to discuss this, right? We have discussed this. A square matrix of all whose elements below the principal diagonal elements are zeros is called upper triangular matrix. That is, for Aij, generally this can be explained as, if Aij equal to 0 for every I greater than j. That means that here, if you consider this is a general matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. That means that the first subscript is greater than second subscript, then that must be 0 here. This is A21. A21 is 0. A31 is 0. A32 is also 0. So based on this general concept, that means that below the principal diagonal elements are zeros. then this is called upper triangular matrix. Upper triangular matrix. Here, the dear students, you have some confusion in this upper and lower triangular matrix. Upper and lower triangular matrix. Here, upper triangular matrix means above the entries are non-zeros. Or another way, below the principal diagonal elements are zeros. That is called upper triangular. Above the principal diagonal elements are zeros. That is called lower triangular matrix. For example, a square matrix, all of whose elements above the principal diagonal are zeros is called a lower triangular matrix. A lower triangular matrix. For that is nothing but Aij equal to 0 for every I is less than j. Here the second subscript is always less than, is greater than the first subscript. That means that first subscript is less than second subscript. That is nothing but all zeros, called a lower triangular matrix. For example, A equal to 2 0 0 minus 3 6 0 4 3 0 8. This is called lower triangular matrix. Now what about a triangular matrix? A triangular matrix is nothing but is either a lower or upper triangular matrix. Is either an upper triangular matrix or a lower triangular matrix. Is called a triangular matrix. Now what about a symmetric matrix? Now we want to discuss about what about symmetric matrix, and what about the skew symmetric matrix. Before we are going to discuss about symmetric means having the same. If there is no change in the given matrix, that is called a symmetric matrix. If there is a change in matrix with the negative sign, we get that is called skew symmetric matrix. Skew faces and skew symmetric matrix is nothing but a square matrix capital A equal to Aij is said to be skew symmetric matrix. That is nothing but Aij equal to Aji. That means that if rows or columns are interchanged, then there is no change in the given matrix. That is called skew symmetric matrix. For example, let us consider A transpose equal to A. A equal to AHG HB of G of C. If you change these rows into columns, we get the same values. HG, AHG, HB of second row, second column. G of C is also third column. So there is no change in this matrix. That's why these type of matrices are called symmetric matrices. Next, what about the skew symmetric? If A transpose equal to minus A, that means both are same, but we have negative sign for A, we get a skew symmetric matrix. That is nothing but a square matrix capital A equal to Aij is said to be symmetric if Aij equal to minus Aj for every I and j. Thus, a matrix is said to be skew symmetric matrix A transpose equal to minus A. For example, if all the principal diagonal elements are zeros and remaining with negative signs, vice versa, we get capital A equal to 0, A minus B minus A, 0, C, B minus C, 0. This is called a skew symmetric matrix. If A transpose, this becomes A minus B. This becomes minus A, 0, C. This becomes B minus C, 0. So there is a change in this negative sign. We get A transpose equal to minus A. Then this is called a skew symmetric matrix. Every diagonal element of a skew symmetric matrix is necessarily a 0. That is nothing but Aij equal to 0 or Aii equal to 0 for all values. That is necessarily zeros. If these principal diagonal elements are not zeros, this square symmetric is not occurs. So this is nothing but a basic concept about symmetric and a skew symmetric matrix. Are you got my point? Are you
Yes,
got
sir.
my point? Yeah. Yes. If sum of two matrices is exists only when if the two matrices having same order, the corresponding elements, the corresponding entries of the both the matrices are summing, we get the sum of the matrices. Suppose, for example, let A equal to Aij m plus m by n and B equal to Bij m by n are two matrices. The matrix C equal to Aij m by n is called the sum of the matrix wherever Cij equal to Aij plus Bij. Aij plus Bij. The sum of these two matrices is denoted by A plus B. Thus, A plus Aij by m by n plus Bij m by n equal to Aij plus Bij of m by n. This is nothing but basic sum of two matrices. This is already known to you. This is for reference only or remembrance only. Next, difference of two matrices is defined as sum of negative of another matrix. That is nothing but if A, B are two matrices of same order, then the difference of two matrices is not directly defined. First of all, multiplying with the negative sign with one matrix and summing the two, we get the difference. That is nothing but capital A plus minus B is equal to A minus B is called the difference of the two matrices A and B. Next, in the same way, we have to discuss about multiplication of two matrices. What about the multiplication of two matrices? What is the existence of multiplication of two matrices? Can you, anyone can define multiplication of two matrices? 311. 311.
Sir. Yes, sir.
Can you define the multiplication of two matrices? What are the conditions for existence of multiplication of two matrices?
First row and first column of the first matrices and first row of the second matrices will be multiplied, sir.
The existence of multiplication of two matrices. What are the conditions for the existence of multiplication of two matrices? What are the conditions for multiplications, existence of multiplication of two matrices? Anyone from the class?
It should be a square matrix, sir.
If not, if it is not a square matrix.
The first row elements is equals to the second row columns.
Okay, somewhat better.
First matrix row is equals to the second matrix column.
Somewhat better. Next, then what remaining? Anyone?
The number of
First matrix
columns
must be equal to the number of rows of second
Jay Mohan.
matrix.
Jay Mohan, tell me.
So,
Jay Mohan.
first matrix must be equal to the number of rows in second matrix. So,
Okay. Somewhat better. Next, then what about Vinila?
Yeah, sir. Both the matrix should be square matrices. And first row should be multiplied with the first column of the second.
That is the process of multiplication, ma. Then what are the conditions for the existence of multiplication of two matrices? Anyone from the class? So here the basic, can I spell it?
Yes, sir.
Yeah.
yes, sir.
If the existence of multiplication of two matrices must be the number of columns in the first matrix that is nothing but pre-multiplier of a multiplication, is equal to the number of rows in the first multiplier. Say that is second matrix. Suppose, for example, A, B are two matrices. The number of columns in A is equal to the number of rows in B. Then only there is a possibility to multiplying AB. If BA is also exists, then the two matrices must be are of same order. Vinila, you got this one, right?
Yeah, sir.
If AB and BA are exist only when both the matrices are of same order, that means square matrices only. If the square matrices, if those are not square matrices, then the multiplication of two matrices AB and BA are not exist. So that in that case only, the formulae in our basic formulae, A plus B whole square equal to A square plus B square plus 2AB is not applicable for these matrices. Is it applicable for all the matrices? A plus B whole square, where A, B are two matrices. Then what about A plus B whole square in this case? The formula A plus B whole square exists for are applicable for matrices or not. Based on this multiplication of two matrices, AB and BA both are equals to one another, then only A plus B whole square equal to A square plus B square plus 2AB is exists for matrices also. Otherwise, that is not applicable. That is wrong in case of in connection with the matrices. Okay. So anyway, matrix multiplication exists only when the number of columns in the first matrix, that is capital A equal to AIK M by N and B equal to BKJ N by P. So that means that the number of columns in the first matrix is equal to the number of rows in the second matrix. Then only the multiplication of these two matrices AB is exists. Otherwise, this is not applicable. That means the multiplication of two matrices is not exists, is not performed. Okay. If suppose these two matrices are equal, these two matrices having that condition, that means that the row number of columns in A is equal to the number of rows in B. That is A equal to AIK M by N and B equal to BKJ N by P are two matrices. Then the multiplication of this matrix is ultimately the number of the size of the multiplication of this matrix is nothing but the number of rows in A and the number of columns in B. Suppose, for example, if A is a 3 by 2 matrix, B is 2 by 3 matrix, then resultant matrix is 3 by 3 matrix. If A is 3 by 2 matrix, B is 2 by 1 matrix, then the resultant matrix is only 3 by 1 matrix. So this is the way to multiply the two matrices. If otherwise, if the multiplication of BA is also exists, then these two matrices must be square matrices are of same order. Then only AB and BA are exist. AB and BA are exist. This is the brief discussion about matrix multiplication of two matrices. Matrix multiplication of two or more matrices also. So here capital A is called a pre-multiplier, capital B is called a post-multiplier. C is equal to capital AB. Here A is called a pre-multiplier, B is called post-multiplier of this multiplication. Next, what about the integral powers? Here, up to this, we come across in our previous classes, as either in first year, second year, or 10th class also. You come across this matrix multiplication, then only we have to remember this. Now we want to discuss about what is a positive integral powers of a square matrix. If capital A is a square matrix of any order, then the positive integral power of this matrix is defined as A square is defined as A into A. That is nothing but A square. Then by the same way, A cube equal to A square into A, or A into A square. Similarly, we have to multiply these with A power n minus 1 into A into A power n minus 1, that is equal to A power n, where n is a positive integer. This is called positive integral powers of a square matrix. That means that these multiplication of n number of matrices is exists or not. This is the way to multiply all the matrices. Those must be of same order and having same order or same size. Next, here A power n equal to A into A into A into A n times, and in the same way, this multiple positive integral powers of a square matrix. Identity matrix is a square matrix. Say yes or no. Identity matrix is a square matrix or not?
Yes, sir.
Yes, sir. Yes, sir.
I is nothing but a square matrix, either of n by n or whatever, 3 by 3, 2 by 2 or whatever. I power n equal to I only. I power n equal to respect to addition of matrices. Addition of matrices. What is meant by distributive law? Okay. A, B, C are three matrices. Then A into B plus C equal to AB plus AC. If these three matrices are of same order, square matrices, then only AB plus BA into B plus C equal to AB plus AC. And B plus C into A is also BA plus CA. These two associative laws, distributive laws are exist only when these two matrices, these three matrices are of same order square matrices only. And multiplication of any matrix with identity matrix is nothing but that matrix itself. That is called identity law of a matrix. If A is a square matrix of order n by n, then A into In equal to In into A equal to A. This is one more important concept in our matrices. Multiplying any matrix with identity matrix of same order, then we get only the matrix itself. This is called identity rule or identity property with respect to multiplication. Next, trace of a square matrix. The sum of principal diagonal elements of a matrix is called trace of a matrix. Trace of a matrix, that is denoted by TR of A. Therefore, trace of a matrix, if A is n by n matrix, A equal to A is a n by n, then the trace of this matrix is nothing but trace of A equal to A11 plus A22 plus A33 plus so on plus ANN. This is called trace of a matrix. Suppose, for example, let A equal to A plus AHCHB of G of C is a given matrix. Then the trace of this matrix is defined as trace of A equal to the principal diagonal elements A plus B plus C is called the is nothing but the trace of this matrix. Here we come across some trace, some properties on trace. If A and B are square matrices of order n and lambda is any scalar, then a trace of lambda A equal to lambda into trace of A. Trace of A plus B equal to trace of A plus trace of B. Trace of AB is equal to trace of BA. This is nothing but if AB and BA are exists only. If AB and BA are exists. Next, we come across what about idempotent matrix? What about a nilpotent matrix? What about involutory matrix? Then only orthogonal matrix. These are specific matrices having some basic features of these sets. Suppose if A is said to be idempotent matrix, A square equal to A. If A square equal to A, then the matrix is called idempotent matrix. If A power n equal to O, the null matrix, then that matrix capital A is called null matrix, and n is any positive integer. Suppose, for example, if A power A square equal to 0, that matrix A is called nilpotent matrix. If A cube equal to 0, A is also called A cube equal to O, null matrix, then A is called nilpotent matrix. If A power 4 equal to null matrix, then that is also called nilpotent matrix. So any integral power of A, any integral power of a square matrix is equal to a null matrix. That matrix is called nilpotent matrix. If n is a least positive integer such that A power n equal to O, then A is called nilpotent matrix of order n. If n is either 2 or 3 or whatever, the least positive integer, then only we call this matrix is called nilpotent matrix. Then what about involutory matrix? If a matrix capital A is said to be involutory matrix, if capital A is said to be involutory matrix, if A square equal to identity matrix, then A square equal to I in identity matrix, then this matrix A is called involutory matrix. Next, we have to come across orthogonal matrix. What is orthogonal? If a matrix A is said to be orthogonal matrix, if a matrix A is said to be orthogonal matrix, that matrix satisfying the condition A into A transpose equal to A transpose into A equal to I, then only we call that matrix is that matrix is orthogonal matrix. Orthogonal matrix. So a matrix, a square matrix is said to be orthogonal if A into A transpose equal to A transpose into A equal to I. For example, we have to solve some problems here. Please note it down. Are you having books with books? Students, you have any books or paper and pen? Please note it down. A square matrix A is said to be a square matrix is said to be orthogonal if A into A transpose equal to A transpose into A equal to I, identity matrix. Say, for example, show that A equal to cos theta sin theta minus sin theta cos theta is orthogonal. Dear students, you have to once again in each class, you have to join once again. Then only we have to complete our total syllabus with the effective manner. Otherwise, the syllabus is not completed because this is a useful subject for you. Useful subject for you, and this is a specific mathematics for artificial intelligence and data science students only. So that's why you have to more cautious, you have to excel your profession. In your profession, you have to more cautious in this concept, linear algebra and regression analysis concepts, please. So now we want to solve this problem. Show that A equal to cos theta sin theta minus sin theta cos theta is orthogonal. Let capital A equal to cos theta sin theta minus sin theta cos theta. Then what about A dash or A transpose? Cos theta sin theta in row in column minus sin theta cos theta in second column. This is A dash. Now we want to multiply A and A dash. A and A dash is nothing but A into A dash equal to cos theta into cos theta, sin theta into sin theta. That is cos square theta plus sin square theta in first row, first element. Next, cos theta into minus sin theta plus cos theta into sin theta. That is minus cos theta sin theta plus cos theta into sin theta. That is the second row, second element in the first row. Next, in the same way, multiplying with the second row of first matrix with all the columns in the second matrix. That is minus sin theta into cos theta plus cos theta into sin theta minus cos theta sin theta plus cos theta sin theta. Next, multiplying with the second column, we get minus sin theta into minus sin theta sin square theta plus cos theta into cos theta cos square theta. So the product of these two matrices is nothing but cos square theta plus sin square theta minus cos theta into sin theta plus cos theta into sin theta minus cos theta sin theta plus cos theta into sin theta cos square theta plus sin square theta. Here minus cos theta sin theta plus cos theta sin theta gets 0. Cos square theta plus sin square theta is 1. So 1, 0, 0, 1. That is a 2 by 2 identity matrix. If you multiply A into A dash into A also, we get the same identity matrix. So A into A dash and AI dash into A is also equal to I. So this matrix is called orthogonal matrix. Orthogonal matrix. Next, we want to show that another problem. Are you noted down?